All right, here we go, 7-2. So now we got friction in our type 1 where we got an object that's stationary and an object that's moving. All right, so we got a 14-gram bullet. Remember, 1, 2, 3, so 0.014 kilograms. All right, 121-gram block of wood at rest. That's good. After the impact, the block slides 8.3 meters before stopping. All right, the coefficient of friction between the block and surface is 0.7. All right, how much work is done to stop the bullet and block? Remember now, here, the work is basically going to be from friction, okay? So let me actually annotate that. So this is going to be from friction. So that just means we need the force of friction times delta x. How far did it go? All right, our work from friction here is going to then be mu mg times delta x. All right, so this will be 0.7 times, now, because it's a bullet block combo or sliding, we have to take our mass of both of those. So, this is still grams, so that's 0.121 kilograms. So we're going to take 0.014 plus 0.121, all right, times 9.8, that's our gravity. And then the distance it travels is 8.3 meters, all right? So multiply all those together, 0.7 times 0.014 plus 0.121 times 9.8 times 8.3. All right, our work from friction here is going to be 7.69 joules, okay? How much kinetic energy is lost as the block comes to stop? Well, remember, in this case, there is no applied force, there is no applied work, so the net work is really just our work from friction, okay? So our net work here is going to be 7.69 joules, all right? So in our net work then, this is also our change in kinetic energy, okay? Remember that anytime that we have that network, that is just represented as our delta KE as well, okay? Determine the velocity of the bullet and block just after the bullet becomes lodged in it, all right? So this one we need delta KE equals 1/2 mv squared. 7.69 equals 1/2. And so this will be the bullet block combo because they're still moving. So 0.014 plus 0.121 times v squared. Okay, so 0.014 plus 0.121. All right, that's 0.135 times 0.5. Okay, so we're going to divide all of this stuff by 0.675. All right, so 7.69 divided by that. All right, so we get 113.93 equals v squared. Square root that, v equals 10.67 meters per second. Oops, sorry, I haven't been highlighting answers. There, all right. Calculate the momentum of the bullet and block just after impact. So remember here, this is going to be m delta v. All right. Oh, we probably don't need if it's just momentum, we need that. All right. So P equals, again, this is bullet and block, 0.014 plus 0.121 times that velocity of 10.67. All right. So 0.014 plus 0.121 times 10.67. All right, so the momentum here was 1.44 kilogram meter per second. All right, so determine the momentum of the bullet prior to the impact. Well, this is where it gets interesting because remember, before impact, all right, the only thing that was moving was the bullet because the block was at rest, all right? So because the block was at rest here in the beginning, that means that the momentum of just the block is 0, right? Because this is the bullet and the block together, right? So that means if the block was that, then the bullet has to be equal to the bullet block combo. So that means 1.44 kilogram meter per second is the momentum of my bullet. All right, oops, sorry. All right, calculate the velocity of the bullet before it embedded itself in the block. All right, well, so then if we know our bullet has that momentum, right, that's going to be equal to mv. All right, so 1.44 equals the mass of the bullet, 0.014 times v divided by 0.014. Our v equals divided by, oops, that answer divided by 0.014. We see it should be 102.9 meters per second. All right. Bottom part, 357 Magnum. Okay, so that's got that. All right, so that'll be a mass of 0.158 kgs. It's fired into a stationary chunk with a mass of 20. Okay, similar. All right. The table is determined to have a coefficient of friction of that. But the bullet leaves the gun at 442 meters per second. How far will a chunk of wood travel after it embeds itself? Okay. How much momentum does the bullet have before it impacts the chunk? All right, so if we know that the mass of the bullet is 0.158 kgs, all right, and we know that that's the velocity of the bullet, so the momentum of the bullet equals the mass of the bullet times the velocity of the bullet. All right, so that is 0.158 times 442. All right, so this has 69.84 kilogram meter per second of momentum. All right, how momentum does the chunk have before the bullet impacts it? So just before it, all right. So the chunk is going to equal the mass of the chunk times the velocity of the chunk. So the chunk here, this is 20 kgs. The velocity is 0. All right. So it has 0 kilogram meter per second. All right. Because it's not moving. Okay, so how much momentum does all of it have together? Well, that would be the P of the bullet plus the P of the chunk equals the P final of them together. Basically the BC, all right? So 69.84 plus 0 equals our momentum of our bullet chunk combo. So the momentum of our bullet chunk combo is going to be 69.84 kilograms meters per second. All right. Okay, so how fast is the bullet chunk moving just after impact? All right, so that would be the mass of the bullet, or the momentum of the bullet chunk, the mass of the bullet chunk combo, and then the velocity of those two together. So 69.84 equals 20 kilograms for the chunk, 0.158 for the bullet, and then V. So we'll divide that by 20.158. All right, our V here divided by 20.158 on my calculator. That's going to be 46 meters per second. Okay. All right, what is the initial kinetic energy of the bullet chunk just after impact? All right, so the initial KEI, that's going to be 1/2 m, and again, this is going to be bullet chunk, V of the bullet chunk squared. So our KEI equals 1/2 the 20.158 times the 3.46 squared. KEI KEI equals 0.5 times 20.158 times 3.46 squared. That's 120.7 joules. All right. What is the work done by friction on this? Well, the nice thing is that there is no other work being done other than friction to slow this thing down to a stop. So our KEI equals our net work, which equals our work from friction. They're all the same, right? So our work from friction here equals 120.7 joules. All right. Oh, undo that. Hit the wrong one. There we go. All right. So then how much force of friction is on the bullet chunk combo? Well, force of friction we usually want to use mu mg for, right? So, which should work for us here, right? So we have the mu, again, this is the bullet chunk combo, times g. So our force of friction equals 0.245 times 20.158, that's both together, times 9.8. All right, so our force of friction equals 48.4 newtons. All right, and lastly, how far did the bullet chunk combo travel? Again, that's going to be based off of the work of friction and the force of friction, and then our delta x. So if we know that we've got 120.7 joules there, 48.4 newtons there, delta x there, divided by 48.4, delta x equals 120.7 divided by that. We see this should be 2.49 meters is how far that thing